Yes, easiest one. Why don't you come to my lesson today? 'Cause actually, I've got something interesting today. I guess you guys will come to my lesson.
Radio.
The crystal radio, yes. So this is the crystal radio. Actually, I have put all the things at the back. So if you have chance, maybe I can put it here, so that you can have a look. So it is the crystal radio. Oh, can you see it? Crystal radio. So there are two one point. This point is for putting your antenna in. Okay, putting your antenna like this. Okay, and one side you put your crystal headphone like this. So actually, this is very difficult to purchase now. You can't find it. Maybe you can, but this is a bit hard for you to find it. Okay, I'm not sure if this is working right now because I don't have the manual with me, so I just guess I'm doing everything correct. Okay, so if you have set up correctly, you can listen to the AM radio like this with a setup like this. Okay, so this is the crystal radio. So I can just keep pass it to Cecilia. I'll explain it later time. And how come you don't attend my lesson? Yeah. Actually, I've also bring another stuff with me, because I've put them together, which is a pack of electronics components with me. Because when we go through it, I guess better for you to have a look first before you take the exam. Just to let you know what are they. So, like for example, in our class we always mention something like capacitors, and diode. But I don't have diode here, so I use a LED instead. Okay, so LED. So it is also a diode, as I remember. And let me see. And I guess I have a variable diode here. Is it this one? Oh, a transistor. Transistor looks like this. So just to let you know what they are. Let me check. Oh, they should have included a coil, but never mind. Resistance, they have resistance, which is, I guess this is carbon film type. Okay, so if we have time, we will show you this. Why it is important? Because we are going to talk about the equipment measurement and testing today. So we have our, I bet they don't have battery inside. Multimeter with us. Oh, let me just find the battery. 呢個可能 OT 係咪度？OT 算啦。哦，never mind。Oh, battery。喂。Okay. So before we talk about the measurement, we have always need to talk about the accuracy. So it's a bit like science. It is not included in your exam, but I'm going to talk about it when you do your measurement. So sometimes you have to we have to talk about the precision. Precision is something we'll talk about in our class. Okay, it is included in the exam, like how many ppm, how many percentage, or up to the precision of a scale, okay, in a scale. Like your ruler may have a 1 millimeter, up to 1 millimeter precision, or your, something like this, okay. So this is about the precision, and about accuracy. Sometimes you may have a very, so you see that this these two diagram, okay. The accuracy means how close is your target, okay. So sometimes you may have a very high precision, but it is not accurate. So it will look like this, okay. So sometimes that's why we have to always recalibrate our measuring equipment from time to time. It's because when time passes, the accuracy may decrease. So we have to calibrate our equipment so that the accuracy will increase. Okay. Okay. So we have talked about the resolution. Resolution is how small the units we can measure. Okay. And accuracy is the maximum expected error in measurement. Yes, and when I prepared my materials, I found that they have put a statement like this: the instrument accuracy can be specified in absolute or relative terms. So what do we mean by absolute or relative terms? For absolute, it is very clear. Like in measuring length, it can be 1 cm, 1 mm, 1 nanometer. This is called absolute value. But relative terms, so just as is written, it is about like percentage. Like my accuracy is 5% accuracy. So what does it mean by 5% or 5 ppm? Like I'm measuring a very high frequency, for example, 400 megahertz. So the 5%, I have a good example here. Still remembered our what is it called? Resistance, right? Resistor. We got resistor here. Let me see which one is a better illustration. Just a minute. Because they are all 5 bands. Okay, I guess this is better. Can you see it? I hope you can see it. I will show you this. For example, the resistance here. The last band is in brown, okay? So you can check your percentage, check the chart. Brown is how many percent? Or is it black? Also, you can Google how much percent the accuracy of it. So it's like in percent, expressed in percent. So for example, 100 ohms resistor having a 5% of accuracy. So it ranges from how much? So you can calculate yourself. I'm not going to calculate here. 950 to 1050, around like this, right? 5%. Okay, so I'll pass it here. 睇下啦，係。Oh, they actually give me a bar here. Talking about which one? The resistors. Hey. Okay. So let's continue. Okay. Okay. So when I do prepare the notes, I found that it sometimes can be measured in both. What does it mean by both? It may be 1 ppm or plus and minus and plus or minus 10%, something like this. So I will show every examples to you this time. Okay. ppm. ppm is one of the measurement units will appears in your exam. So ppm means 1 parts per million. So you know that it is 1 over 6 to the power negative 6, 10 to the power negative 6. Okay. Okay. So this cube is an illustration of how 1 ppm is compared with 1%. Okay, and I don't know what is this, but this is 1 over 1,000. Okay, 1 over 1,000. So it is even smaller, 1 PCM, 1 ppm. Okay. Just remember it is 10 to the power negative 6. Okay. It may appear in your exam. Okay. So for example, example 1, we have the RF power meter. They said that it is 5% of full scale. Okay. So it is an illustration of relative accuracy. Relative accuracy. The full scale is 100 watts. Okay. So what is the 5% of full power? Okay. So it is plus or minus 5 watts. Okay. But they create a problem. If you are not using a full scale, like 100 watts, like you are just using one tenth of it, 10 watts. So it could still have an actual power of 5 watts to 15 watts. Okay. Easy to understand, right? I guess it is easy to understand. Let me bring my iPad with me. Another example of relative accuracy. So it's very easy to understand what is absolute accuracy, right? So it's just plus or minus a number. Relative accuracy of 3%. Okay. So accuracy of 3%. So you know that for 1 watt, it is plus or minus 0.03 watts, and for 110 watts, it can be up to 0.3 watts. So how come they have a difference? It's because of the description. So you have to pay attention to the description. Okay. Okay. So what is the difference between the description? So you see that the first one, RF power with accuracy of 5% of full scale. So for full scale, 5%. So you have to find out what is the power at full scale first. Okay. But for example 2, it just mentioned that the accuracy is 3%. It didn't mention other information to you. So it is 1 watt and plus or minus 3%, which is 0.03 V. And for 10 volts, it is 0.3 volts. Okay? Okay. Okay. Just a minute. Let's see. Okay. Example 3. Okay. Which is a combination of absolute and relative accuracy. What does it mean? You see that from the example of textbook, it may appear description like this: 1 ppm plus 1 count. Okay. But this is not that common in exam. I guess. Just a minute. How come I cannot control it? Okay, good. Plus or minus 1 count. So you see that what is 1 count? This is just plus 1, okay? 1 ppm. So you have to calculate what is the accuracy first. For example, like 10 kilohertz signal with 1 hertz resolution. 1 count is 10 ppm of 1. Okay. Okay. 100 kilohertz. What is 10 ppm? So you can calculate. Do I have to do the calculation? Okay, I can do the calculation. Just a minute. Okay, great. So for example, they mentioned about 100 kilo, yes, 100 kilo. 100 kilohertz. accuracy is 10 pp. No. Is it 1 ppm? Oh, okay. 10 ppm. 1 count. No. Okay. Because I didn't see it in my exam. No, I'm in my previous classes. 1 count. 咦唔係喎 1 count. Never mind. Just keep it. 1 count plus 1 ppm. And we told you that 1 count is 10 ppm of the 100 signal. So 10 ppm. 10 ppm of 100 kilo, 100 kilohertz. How to calculate it? ppm is yes. Okay, so you can do the calculation. 3加2 5. Am I doing the calculation wrong? Let me see.好似係計錯數 ，kilo 係1000， 3加2 5。咦 ？Wait. Oh my god！ 唔怪之係計錯數啦我。This multiplication。So you see that no, it is more than 1 kilohertz, 1 hertz. Okay. Okay. So for this one, this is like accuracy of 10 ppm, but it is 0.1 count, so you know that the accuracy is 11 ppm plus or minus plus 1 count, right? So you can do the calculation. It becomes 1.1 hertz. You can do it either yourself. I don't do it. Test equipment. But what I'd like to tell you is this description may not appear in your exam, but the concept of ppm is commonly used in frequency. Measuring the frequency, because for the frequency measurement, all the frequency have a very huge number, like they are kilohertz or megahertz. So often they are using ppm to defining their accuracy. Okay, so if they ask you about questions on like frequency counter or oscilloscope or that kind of stuff, just ask about frequency. There is a very high chance for you to see words like ppm. Okay. That's why you know how to do the conversion. It's easy, huh? It's just 10 to the power -6. Okay. Okay. So when we talk about all the testing equipment, it's actually just the revision of the very basic concepts of our first lesson 2 to lesson 5 about basic concepts of electricity. Okay, so still remember what is Ohm's law, right? Ohm's law like this. It is V equals to IR. Hey, V equals to IR. And okay, what I really want to talk about is just a minute. How come my pen is not working well today? V equals I R, right? So what are they? V is voltage. What is I? I is current. What is R? Resistance. Okay. So if we have a constant resistance, R is constant, voltage decrease, current will increase, okay? Or in reverse way, voltage increases, current will decreases, okay? Similarly, if V is constant, I increases, resistance increases, current will decrease, okay? This is what Ohm's law talks about. Okay, so we have three components here, right? Voltage, current, and resistance. So we have different kinds of measuring equipment to measure them. So very simple. For measuring voltage, it is voltmeter. Current, it is ammeter. Resistance is ohmmeter. But most of the time we are talking about multimeter. Okay, which is the one I've just showed you earlier time. This one, which is a digital one. They don't have battery inside, so I can show you how to use it. Okay. So voltmeter. We measured. Still remember the keyword potential difference. The word potential difference means voltage. Okay, they are just equivalent in electric circuits. Voltmeter must be placed across the component or source of voltage to make the required measurement. Okay, so in our diagram, I've just showed you that. Like for example, we are measuring this resistance or measuring the battery. We have to put the voltmeter parallel with them. Okay. What does it mean? Like if we have a light bulb here, we will have to put our voltmeter. Let me use a red pen. Across them, okay? Across. It's parallel. Okay, parallel. And one of the characteristics of voltmeter is it should have a very high resistance. Why we have a high resistance? It's because we have to still remember V equals to IR. If we have a constant V and have a very high resistance, the current will decrease. Right? So this part of it will consume very low current. Okay? It will have a very low current pass rate, so that it won't waste a lot of energy on the voltmeter. Okay? Yes, and it's yes, we won't put it in the circuit. We would put it parallel. Okay, parallel. And ammeters is current meter. Okay, so voltmeter we put it in parallel, and ammeter we put it in series. Okay, in series. So compared with voltmeter, the emitter should look something like this, okay? Let me put it side by side so that we can compare. Okay, we'll put it inside the circuit. Put it in serial, okay? Put it in serial. And compared with the voltmeter, the ammeter will have a very, very low resistance, okay? Very, very low resistance. So that most of the current will pass through it, okay? And it tries to just a minute. Okay, I should put it this way. Still remember that we have the Cherkov's and Cherkov's current law. What does they talk about? The voltage law tells us about in a loop, the voltage drops across what? Just a minute. Okay, let me put it into it. The voltage consumed by this component and this component in a closed loop should be equal to the voltage of the source. This is KVL, Cherkov's voltage law tells us. And for KCL, it's about current. Let me find a description later time. I forgot it. I really forgot it. Okay. Oh, it should be similar in a parallel circuit. Never mind. Let me check it in during the rest. Okay. Okay. What I want to tell you is, this component, it will consume voltage. It will cause a voltage drop. It will cause a voltage drop. In a closed loop, the current is constant. The current is constant, right? The current is constant. So that the constant current will flow through the ammeter and the light bulb. Okay? The current inside this loop is always a constant value. Okay? Only the voltage will drop. So that if the resistance is decreased and I is constant, just a minute, E equals to I out, right? So when R decreases, the V will also decreases. So that the ammeter will just consume a very, very little amount of voltage. Okay. So theoretically, the ammeter should have zero resistance, so that it will not consume any voltage. Okay. Yeah, I remember it. Okay. Just a minute. Let me put it down. So we have different cases. So I guess you can memorize it first. Okay. Okay. So for a parallel, this is a parallel circuit, right? The voltage pass through them as the same. Okay. They mean as V1, V2, V3. V1 equals to V2 equals to V3. Okay? Let me have a circuit like this. Just a minute. So that when you measure the current in a serial circuit, so you will measure that I1 equals to I2 equals to I3. Okay. Okay. And this is KVL, this is KCL, yes. Is what? Okay. So the KCL mentioned that the I across okay. KCL mentioned that I1 plus I2 plus I3 equals to total work. And KVL mentioned it like this is V1. Let me have a simple illustration of it. V2, and this is V3. V1 plus V2 plus V3 equals to V. Okay. So you have to, if you can't remember the name, just remember that voltage is constant in a parallel circuit, and current is constant in a serial circuit. Okay. And why this works is because of Kirchhoff's current law and Kirchhoff's voltage law. If you can memorize it, just memorize it. If you can't, just forget it. Okay. Just remember the fact. Okay. It should name like the CHOF. I guess I mentioned it in lesson 3 or lesson 4. So see if you can remember it. Okay. Okay. So there is one more point to add in this slide. So you can see that note that the circuit must be, if you don't have the ammeter inside your circuit and you have to add an extra one to it, you must break the circuit first. You must break the circuit first, and like intercepting the circuit, intercepting it, okay, and complete electrical path. If you don't have the ammeter intercepting it, you can't complete the circuit, and no current will flow through the ammeter, okay? Or no current will even flow through the whole circuit. Yes. Okay. And last one, ohmmeter. Ohmmeter is the easiest one. Just to measure the resistance of it. How do you measure it? Take this one, you take this one with you, and you take your ohmmeter with you. Because the resistance itself don't have a polarity, so you can measure in both ways. You just take out your probe and measure like this. Yeah, that's all. Take your probe, connect to N, and you can measure the resistance of it. Okay. But there's one point you have to note for the ohmmeter. You must disconnect the power first. Disconnect the power first. Okay. Two main reasons. One is if you have the current, the circuit is a closed circuit. It is working circuit. Okay. If you intercept it, you may accidentally shock yourself, or you may have inaccuracy in your measurement. So that's why you have to either break your circuit first or turn off the power first. Okay. Yeah. For safety and accuracy problem. Yes. So you can you see why. Okay. And yes. The accuracy is because if you don't break it, like in a parallel circuit, the total resistance may be a bit lower than it is expected. Okay. Yes. There is one point to note down. semiconductors will have a greater resistance of one side. So still remembers the voltage ampere characteristics of semiconductors. So it have one side higher resistance and one side is lower resistance. So you can measure by measuring the two sides of it, you can confirm the polarity of the semiconductor. Okay, easy, huh? Okay, let's continue. Okay, this is how you check the resistance of it. Okay, this part is the whole ohmmeter, and you have two probes here. You just put the probes over the tip of the resistors to measure its resistance. Okay, you don't have to memorize this one, but just to bear in mind that ohmmeter needs power, needs voltage, needs battery to power. Okay, if you don't have a battery inside, you can't measure the current and measure the resistance accurately. Oh, I didn't mention it. Okay, for some old type of the ohmmeter, let me grab a diagram very quickly. No, it's not a good diagram. Oh yes, great, this one. So if we have a ohmmeter in hand, like this one, right? You have knob to set infinity or to reset set 0. Okay, so so that's the ohmmeter may the readings may not be accurate from time to time. So that you can use the knob to recalibrate before your measurement. So that how to do so for this kind of analog meters, how can we do the calibration? Just a minute, let me. So you can just put the tips together so that it creates a short circuit. So in this form of short circuit, like this. In the form of short circuit, the reading should be 0. It should be 0, so that you can turn the knob and set it to 0 before you do the measurement. Okay. So sometimes the ohmmeters may have an extra knob for you to change the range of measuring the resistance, and this needle will the needles will not be 0. I don't know why, but just to let you know, if you have time, if you have chance to do it, you can try it. Okay. But nowadays they don't have a lot of analog ohmmeter or analog multimeter now. Most of them they are using digital. Okay. Yeah, but I guess Michael should have analog multimeter in his hand, so you can ask him to borrow you. Yeah. Okay. So multimeter. So we don't want to buy a voltmeter, ammeter, and ohmmeter from time to time. So it takes up space for measurement, right? So that's why people decided 3-in-1 meter, which is multimeter. So they can measure. Yeah. Let me show you. Just the WhatsApp. Just a minute. Thanks a lot. Hey. 點解我 show 唔到？Hey. Like this. okay, which is old, very old type of, no old type, analog, a very traditional, typical analog multimeter. So you see that it has different functions. You have a calibration block for calibration, okay, and yes, okay. I'll use this. I need this diagram. Thanks a lot. I need this diagram for some illustration. Okay. So for multimeter, it can measure voltage. It will measure resistance. It can also help to measure the current, the ampere. Okay. Okay. So if you have chance to play with it, there is some extra things to bear in mind first. So for this kind of readings, the basic one is voltage, ampere, and resistance, right? And they got different ranges, especially for the digital one. Okay. For voltage, if your multimeter can use to measure alternating current, you have to bear in mind which side is alternating current and which side is direct current. They have different symbols, okay? So if you don't want to, if you can't use, or you can't, no, you don't want to use DC mode to measure the alternating currents. Two main problems. One, the major problem is it will create inaccuracy. AC is a very it's an alternating current, so it is switching from plus 300. No. Oh, so you can multiply 280 something times 1 times 414. Okay, 280 something or 260 something to negative 260 something. So your multimeter may not be fast responsive enough. So it may have a 0, okay? Or it may always measure the peak instead of RMS. Still remember what is RMS? Root mean square. Okay, which is when we want to compare the actual voltage that can be used in AC. How should I address it? The equivalent voltage of DC, the equivalent voltage of AC compared with DC, okay, the RMS. Okay. So only the AC mode will help you to measure the RMS instead, okay? Prevents the inaccuracy. And for some kind of new type multimeter, it can also let you measure the semiconductor. So you see the NTN keyword here. It can just insert your semiconductors, like your transistors, to measure the readings of it. Okay. For some meters, I remember that it can also let you measure the capacitance. It can also help to measure the capacitance. Yeah, I'm not sure about the inductance, but it may have. Okay. Okay. So let me put it aside. So we have mentioned what is the multimeter, and there are some new types of multimeter, which we call clamp meter. So the clamp meter makes use of the induced current. So still remembered for wires that carries that have current pass through, it will have a magnetic field surrounding it, right? So the clamp meter is measuring the, I'm not sure which one is there measuring, but it should be the magnetic field. So by measuring the magnetic field, it can using it in direct way to measure the current in it, so you won't shock yourself. Or in sometimes you really can't break your circuit and insert the ammeter inside, right? So we can use a clamp meter to use a not intrusive way to do the measurement, which helps a lot. Yeah, especially if you are doing high voltage stuff. Okay. Wattmeter. Wattmeter is the power. Still remember the formula. Power equals to voltage times current, which is the measurement of energy used or consumed by the electrical components. So we use a wattmeter to measure how much energy is being consumed. For example, still remember in our license, we mentioned that, hey, our signal should be how many dB watts, that kind of stuff. So we can do the measurement using a wattmeter. Yeah. Okay. Wow, 出事，成日講下家長。Okay. So AC measurement. So I actually have talk some parts of I've introduced some parts to you already. Okay. AC. So we for alternating currents we have different values. Peak to peak. Peak, RMS, and average. Still remember how do we measure different numbers? Let me try. Actually, I want to explain it once again because it is quite important when you want to, if they ask you about it or compare it with the DC. So this is DC in yeah. This is voltage. This is time. So saying this is 0. Let me have ask you a quick, very fast question first. So do you remember what is the frequency of the electricity in Hong Kong? It is 50 Hertz. So how much time does it require to travel one cycle? Okay, so the time here is 0.02 in unit of seconds. 1/50, you can calculate it yourself. Okay. So I have introduced to you different kind of measurement, right? The first one, let me minimize it first. This is peak to peak. Okay. This is peak. So what is the relationship between peak and peak to peak? Peak to peak equals to 2 times peak in AC form. No, in a sine wave, in a perfect sine wave, okay? It's 2 times peak. How about, let me use another color. Let me use orange. So what is RMS? And average? Oh, this is RMS and this is average. Because when I study, I found it myself easier to memorize the definition, so I didn't memorize the numerical value. RMS equals to 1/2, which is approximately 0.707. Okay. Average. Okay. Let me just make up a value first. Times peak. And average, which is 2/pi, which is approximately 0.61 something times peak. Okay. Okay. I'm wrong. Just a minute. This is 0.637. Okay. So in case they really ask you about the voltage, you have these 4 different values in your mind: peak to peak, peak to peak, peak value, RMS, and average. Okay. So the 220 volts in our daily AC circuit is actually the RMS value. So you can calculate what is the peak value. Now you can try. How do we do it? Say we already know that RMS is already equals to 220V, right? Then your peak will be equals to 220 divided by 0.707, or we say that, let me just do it, divide by 1/2, which equals to 220 divided by 0.707, which will result in, just a minute, 220 divided by 1/, which is 311. Okay? It's that easy. Yeah. You don't need it. Okay. So there is one reason why we yes. Let me talk something different. Okay. So the RMS value, why it is divided by 1/2, is because we just make use of a sine wave and we do calculation of it. We do the root mean square of every value. So it is a bit it's actually from the definition of integration. Okay. So if you make complex waveform, you can't do the RMS value by doing peak divided by 1/2. You have to do the integration yourself. Okay. So bear in mind that every questions in our exam are doing sine wave. So that's why it is 1/2. If one day you do the measurement, it is no longer 1/2. It is no longer a perfect sine wave. You need to use integration. Okay. Like if you use square wave, you have sawtooth. We have triangle wave. No, it is not 1/2. Okay. And let me see. Let me see how much size still we have first. Okay. I will talk until RF measurement, okay? Before we have a break. Okay, so I may need like 15 more minutes before we take a break. Frequency and time. Still remember how can we change between frequency and period? Just one over, right? So you have you know what is the formula between. So to measure frequency, we have frequency counter. I'm not sure if there are any staffs coming back later time. Actually, we have a frequency counter in hand. Okay. So frequency counter is very sensitive to signals. Okay, but it will only measure the if we have a frequency counter like this, like they have a range. Okay, so they will just choose the strongest signal to receive. Okay, give you the count number. Okay, give you exact value of the highest frequency that you are receiving now. Okay, so for example, if you have two signal sources using two different frequencies, the frequency counter will just give you the one having the highest number of highest strength. Okay, highest signal strength. Okay. There are two different kind of frequency counters. Actually, the description is written in the previous slide, which is the first one is a handheld one. The second one is have a probe, so you have to plug in your connection cables, the coaxial cables. Okay, so this one is easy. If you have a signal, if you have your radio, you can just connect your radio to the frequency counter, so that you can always measure, hey, if I'm transmitting the exact frequency that the radio says between the antenna. Okay, for the calibration to checking. Why we have to always check our frequency is because by doing so, we can confirm that we are not using, you are doing the desired frequency that we want. We are not interfering others. Okay. And the one on the left hand side is a bit more not advanced, but interesting. I would say interesting. I would use interesting. Okay. It's because they have a little antenna here. They can sniff the signal, so you can, hey, if there's someone using a handheld radio, you can just use the frequency counter and stay beside, and they will give you what is the exact frequency that the guy is using now. Okay? So actually, it is not limited to radio, but sometimes if you have some stations like emitting the TV signals or phone, okay. What is the word? Let me figure it out. I forgot. Never mind. Just you know the 2G signal or 3G signal. So you can use the frequency counter and state the signal. Okay. And the frequency is no. I mean, the accuracy is measured in ppm. Okay. Then also the oscillators, if they are using the frequency, then you know that it is always most of the time it is parts per million. So you can calculate it. If they say that, hey, my frequency oscillator or frequency counter have accuracy of 1%, so you know that actually have a very high. It have a very low precision. You know that, hey, 440 kilohertz or 440 megahertz, 440 megahertz, 1% accuracy. So you see the range. How much is it? It is like plus or minus 1k megahertz difference. So it is a very huge difference, right? Or 4. Yes, 400 kilohertz, then it is 4k megahertz difference. So that's why they use ppm. They want to limit this accuracy into like 1 to 2 hertz. Okay. I have a video in hand, so I can give you a very short clip to watch.
Good morning. Good morning, everyone. My name is Greg, and my call sign is VE6G. Today's video is related to Amazon shopping.
In one of the earlier videos, you see about some oils. Quick look, you can some radios that were commercial grade. I can't tell what frequencies are on. So I bought this to be able to do 3 radios, key up next channel and see what it shows. So stick around for 5 minutes and we're going to sit. So this is a simplex frequency, and see how well this is. So I can't really hear you, and I'll do the same look for you. How accurate this is. So branch of simplex, which is 146.520. So 146.598. So that's pretty close. That's very close for accuracy. We're going to get up to it. But as I say, this actually is not transmitting the 146 that 519. So we don't know. But for now, that works close enough. We're very pleased with it. So there's the internal battery. You can also see on the side here what the memory was. So that's pretty awesome. You can also pick up CT series codes as well, if you're looking at different things on the side.
Okay. I guess. Yep. The speakers in CSSC is broken, so you can see a bit. They will do the measurement. Just a minute. Let me do it once again. Hey. So when they do the transmission, pressing the button, this little gadget, the frequency counter here, will show you what is the frequency is exactly using, right? It is 146.599. Okay. Here it shows the readings. Okay. Oh yeah. Which is very close to what Ieyasu, the handheld radio, is claiming itself. Okay. So we have talked about frequency counter. The problem with frequency counter, as I just mentioned before, it can just show you the strongest signal. If you have multiple signals, like if you there is always one joke in the ham society, okay? The 暴風 okay? 暴風 暴風 it is a joke. Very cheap handheld radio, and the signal of it is really bad, okay? Let me check if I have the slide with me. Just a minute. Yeah, I mean that doesn't mean slide, but yeah, I got it. 有冇添咧？Yes, this is what we in the ham society we call the 暴風 okay? The 暴風. Very cheap, but the frequency is not very accurate, and did have weird signals. No. Let me show you later time when I have time, when I have stop break. Okay. Okay.
How cheap would that be?
$100.
Huh?
Yes, $100. That's why they use it for DIY. They use it for DIY. Yes. Yeah, I can show you. $100. I'm not joking. Really, 108 RMB. That's why the people in the foreign countries love to make use of it and use it and do the DIY. So this is a very cheap, very basic. Oh, just a minute. Yes, okay. Very cheap and basic transmitter. Very cheap, have basic functions, so you won't lose a lot if you really broke it. Okay. Yes, this is we call the 暴風.
It explode.
No. It is a very low power. Yeah. So we have talked about what is frequency counter. So it has to talk about absorption wave meter. So absorption wave meter, you see that it have a lot of description here, right? The concept behind is very simple. How simple? A radio. But instead, for radios, so you are using headphone to listen to signal strength, right? But for absorption wave meter, the headphone jack is replaced to a meter, so that you can measure the signal strength. Okay, so they call this is the absorption wave meter. Okay? Easy, but you may see that. Hey. Yes. Okay. So they have a dial for you to change the frequency. They have a dial for you to change the frequency. So for radio, you're absorbing FM radio from 88 megahertz to 108 megahertz, right? So similarly for absorption wave meter, you are doing the same. They give you a dial here to change the frequency, so that you are always listening to a target frequency and check its signal strength. Okay. But you see that there are different coils with it. So this is for you to change the antenna to switch to the target frequency that you want to receive. Okay. Yes. So still remember when we talk about the crystal radio? Let me bring the crystal radio with me. Thank you. 呢個 crystal radio. Yeah, this is a headphone. 綠色嗰條係 antenna. Thank you. This part. What is this? This is the coil, right? And what is this? This is actually a variable capacitor. So combining the coil and variable capacitor, this is a LC resonance circuit. So that you can change your target frequency and listen to it, or to analyze it. Okay. So that's why if you match resonance circuits in your exam, don't panic. It is same as this is just the circuits for you to tune in your AM radio or FM radio. Okay. They are equivalent. Or we say we make use of the resonance circuits to tune our frequency. Oscilloscope. Oscilloscope is really important. Actually, when I prepared the notes, I found that I really missed out something that is very important, and it will appear in your exam. Okay, so oscilloscope, it helps to, it tells you what is the characteristics of the whole curve, okay? So we have analog and digital, but yes, most of the time if you see oscilloscope, it looks like this, okay? They have different styles for you to tune your circuits. Actually, they have two main functions. You see the signal, the waveform, you can tune your frequency, seeing which frequency you are going to measure, or the frequency strength, which is the y-axis. Okay, the x-axis is the time, or we say frequency. Okay. Yes, there are some in the past, when PK prepared the notes, he mentioned that frequency counter or frequency counter, it is measured in the frequency, but the oscilloscope, the unit is usually in time, in seconds. Yes, it's true. It's true. Why I know that? It's because it appears in my exam. Yes, so I know how they make the exam. Yes, it's true. So remember that. But so we throw away the examples. In reality, like is this kind of advanced oscilloscope, they will not just show you the time in different divisions, but they will also tell you the frequency. Yeah. So if you have a chance to play with the oscilloscope, you will know that hey, it will calculate the frequency for you. So it's a slight difference between the exam and your actual work. Okay. So for some more expensive oscilloscope, they will support multiple channels input, multiple channels. So you can see multiple waves appears on your oscilloscope. Yes, this is a very old oscilloscope. So I will show you how it works.
Okay, this video is a documentary of a project that I did with the local Grand Club. Went to one of the meetings there and talked about a couple of ways you could use the microphone here. You can see they are on pretty easily right here on the scope. We go through here, and let's try to speed the speedway up here. Okay, you can actually see the carrier. Okay, so we can actually look to see if there's any distortion in our carrier. Because by speaking into the microphone, we can actually see the amplitude modulation of our carrier, because the transceiver being AM mode. As we slowly stroke back down again, so we'll go down to 1 or 2 milliseconds per division. And now, here, and speaking into the microphone, we can actually see the amplitude modulation of the carrier. And kind of make some measurements, or at least make sure we're not flat topping, and take a look and see if there are those little bright spots when I get really loud in the microphone means we're getting pretty darn close to 100% modulation, but you can still see that pretty easily. So now if we take a look at the other channel, we'll go to channel 2. This is the arc detector, so if I just key up, you see the amplitude just goes up here. Okay, and we're in AM mode here, so again if I go in and talk to the microphone, I literally was doing an amplitude detection of the RF signal. So I can literally see my modulated tone, kind of, or AMD mod of my signal, so very easily.
Okay, so this is how you use the oscilloscope, but no but. Let me check it. Hey, oh yeah. I remember that. This is important. This will be asked in your exam. So you have to bear in mind how to read the oscilloscope. Okay. So in reality, you have two nodes. One is for changing the seconds per division. One is changing the voltage. Okay. So what is one division? One division, which means excuse me, which means one square. Okay, one square. Okay. So seconds is the x-axis, and the voltage is the y-axis. Okay. So how they will ask you in the exam? In my exam, I don't know why, but they asked me 3 questions on how they read the oscilloscope. Okay, so I have to talk about this. I really nearly forget it. Okay, so so one cycle. Okay, so they will ask you, hey, the oscilloscope peak to peak, this is one cycle, so you can measure it. Hey, how many divisions does it require for the sine wave to complete one cycle? It is 1 division, 2 division, and 3 division. Okay, 3 division. So at that time point, you know that how many seconds is used. So it is. So you know that 1 division is 1 milliseconds. 1 milliseconds. Okay. Okay. 3 divisions. 3 divisions. Let me grab my iPad with me. Oh, let me do it side by side so I can do it easier. Okay, so it looks a bit like this. If I have a sine wave, so it is measured something like this, right? So sorry for a bad drawing, okay? So you see that it takes 3 divisions for a single cycle, and 1 division is equal to 3 milliseconds, okay? So you know that they will ask you, hey, what is the period, time, or frequency of it? So how to calculate the frequency? We know that frequency equals to 1 over period, right? So which is equals to 1 over 3 times 10 to the power milli is -3, right? So by doing some easy calculations with the help of Google, or so that's why you have to bring your calculator. If you don't have your calculator, just borrow from others, okay? Which is equals to 3 times 3 times 3 hertz. Okay, this is how you do the calculation. Yeah, they can ask you about this, okay? Or ask you, hey, how much time does it takes to complete 1 cycle? They may ask you frequency, or they can ask you time, or they can just ask you about how do you do the readings. Yeah. Okay. And for voltage, how do you do it? Voltage is much easier. Okay. So you see that it is. They will give you this value. They won't give you a diagram like this. They will give you a value besides, telling you, hey, how much is 1 division? How much is 1 division? Like this one. 1 division is 50 millivolts. So have to do the readings. Okay, so let's see how much division it takes for the peak to peak. 1, 2, 3, 4, 5, 6. 6 divisions for peak to peak. So it is 3 divisions for peak. Yes. Yes, my drawing is good. Okay, so they tell you this one division. How much is it? It's 50 millivolts, right? So you know that hey, it is 6 div, 6 division. So the P to peak voltage is 300 millivolts, which equals to 0.3 volts. Okay. So what is the peak value? The peak value is 0.15. Okay. This is how you do the calculation. Why I don't prefer to do the countings from middle to the top? It's because sometimes, hey, if you have really half the reading, or they will give you questions like the peak it's exactly at division, so it will be easier for you to calculate. Okay, like if just the peak to peak takes 5 divisions, so you won't want to count. Hey, the peak value is this just consists of 2.5 division. It will make your readings much more hard. That's why I prefer to read the peak to peak first and divide by 2. Yeah. And if you have even more trickier questions, they can ask you, hey, what is the RMS? Or what is the average? So you can just do it yourself, okay? Easy. Yes, correct. Just a minute, let me do the 0.15 times 0.707. Yes. Yes, that's why when you when I have the example here, they will talk about the RMS is 106 millivolt. That's because 0.15 times 1/√2 is 0.10605. Dead meter. Yes, this part is important. The oscilloscope is important. Okay. Dead meter. So actually, it is the dead meter is measuring which frequency they are oscillating at. Okay. So you see that, hey, using the inductance or capacitance to check what is the oscillating frequency. Okay. Let me show you the video. Actually, it is a very long video, so I'm just going to show you a bit.
Introduction and demo of a solid-state dead meter. This is a more modern version of a meter that's been around for ages called a grid dead meter. And really what it is, and so you're seeing it, there's the gauge up there in the front. Okay, so here's the circuit I'm actually going to look at. This happens to be a 0.22 microfarad inductor, so a little multi-inductor there, and a 220 picofarad capacitor. Now, if you run through the math on this, you find that this will oscillate, or resonate, I should say, at approximately 22.5, 22.7, 22.8 megahertz. Okay. So let's go take a look at that. Now what we want to do is couple these inductors together. So you don't want to kind of go crossways. You want the coils to kind of be parallel to each other. So either like this or in line. What I did is I put a little J hook on the end of this coil so I can kind of stick it right into the coil here so that it kind of does with one hand. So what we'll do is we'll turn the meter on. Okay. And we're going to adjust the oscillation level. Okay. Look at a reasonable value. Okay, let's kind of give us about 70% here. Now we adjust the frequency. Okay, now in this case, the coil we selected is actually the grown coil, so we're looking at the grown scale here. Okay, and as we adjust the frequency of the oscillator, we can take a look at what the meter's doing. Okay, and notice I'm rotating this up, watch the meter, and as I pass through resonant frequency, the meter dips, now it comes back up again. So keep going up, now it's going back up. When I come back down in frequency, okay, it dip, came back up. And that's really how you use this. You find that frequency of that dip. Now it's right about there, okay. Now we'll take a look at the scale here, okay. It's showing between 22 and 23 megahertz. Okay, now these scales you can't really get better than maybe even a couple percent, 2 or 3, maybe 5% accuracy. So we'll call that between 22 and 23 megahertz, which is what we expect. We expect about 22.7, 22.8 with that component combination. Now what we can do.
Okay, so this is how the dip meter works. Okay. So if you want to know more, you can just check the whole video. So let's take a break first. Okay, let's take a break first. Spectrum analyzer. So I have just talked about what is spectrum analyzer. So if you remember what is the diagram after I've shown you about Baofeng, it is actually the spectrum analyzer. So it is similar to oscilloscope, but it present a graphic view of a spectrum, electrical signal. Okay. So in general speaking, spectrum analyzer shows you the frequency. Okay, it uses frequency as measurement, but oscilloscope shows you the waveform. Okay, so they are a bit different. I'm not going to show you. Maybe I can show you a bit. Yeah. So when you just see the Baofeng earlier time, you see that hey, it is the measurement of the frequency. Okay. Yeah. Yes, it looks a bit like this, okay? Let me mute the signal. Yes, in the diagram like this, okay? So this is the frequency and this is the signal strength, okay? X-axis, frequency, Y-axis, signal strength, okay? So it's very similar to oscilloscope, but it is frequency based, and oscilloscope, it is time based, showing the whole waveform, okay? But nowadays there are some oscilloscope can also do the work of spectrum analyzer. Okay. RF generator. RF generator, so it will generate a signal of a target frequency. So why it is used is because sometimes, hey, well, we want to use a signal. We want to check our receiver if they can receive the target signal, or if the readings of the signal and the readings of your radio matches or not, for calibration, okay? And for sometimes, hey, this RF signal generator can also do the AM and FM modulation. Yeah. So it is a testing to test the oscillator or to test your receiving devices. Okay. So as I just mentioned, this one you have to calibrate it before you use, right? So also for the oscillator frequency counter spectrum analyzer, you have to calibrate it after you use it for some time, like for years. So you have to calibrate it. Dummy load. So this one is actually the frequency it shows. Okay, I've give you a illustration of it. Dummy load. We have talked about it many times in our previous lessons, but we didn't have a slides to talk about it. Okay. This is a copy and paste error. Okay. Dummy load 50 ohm resistor with a coaxial connector. Okay, so this provides a flow SWR, like it absorbs all the signal, and for you to test your radio or transmitter when you try to emit the signal. Okay, dummy antenna, very low signal to signal standing wave ratio. Okay, and there is common point characteristics. The points to note. For dummy load, you can't use wire rounded type of resistance, okay? Because wire rounded type will have inductance. This is a coil. This is a coil, so that it will emit signals like an antenna. That's why you can't use wire rounded type for dummy load. Okay, dummy load look like this. Okay, so it has different size, and the one that we have shown you in class is a smaller one, and I guess Rudy have or UPK have shown you a very big one, yeah, a big one. So for even bigger one, they will immerse it with oil, yeah, to absorb all the heat. Okay, because resistance may have a thermal high coefficient like 500. No, I mean the resistance may change when the temperature increase. Okay, that's why for this type of dummy load, they will heat it up and they will tell you what is the maximum emission time they can withstand, like 30 seconds, 10 seconds, that kind of stuff. Yeah, and maximum power. I guess we have exactly this one in our radio group. Use of dummy load. I'm not going to play this video, so if you want to watch it on your own. Okay. Antenna system measurement. Okay. Field strength meter. So it picks up the radius signals from air and indicates on the meter. Okay, telling you, hey, what is the E field strength? The yes. E field is voltage, okay. RF field strength, okay. What's cm squared? Hey, this is about safety. So still remembered in our Annex B1, our ASL, our license. There is a part measuring the safety precautions. So if you know that you are under the RF the radiation, and if your field strength is too large, you should leave this place. Otherwise, you have safety hazards. Okay. This is for you to help measuring the signals, the field strength. Okay. Yeah. And we have to talk about SWR meters. SWR meters is again one of the instruments measuring equipment that we have talked about, but we didn't go through it in detail. So still remembered how we do the SWR. When we have SWR mismatch, the impedance mismatch, we have a forward power to the antenna, and they will have a reflected power back to our RF device. And if the standing wave ratio is too large, it will risk damaging your radio, your device. Okay. That's why we want to match our impedance 50 ohm to 50 ohm as close as possible. And the calculation of SWR is like this one. 1 plus root of power reflect over power forward over 1 minus root of power reflected over power forward. This is the equation that you should memorize. Okay. They may ask you in your exam, because I forgot if I have made this question at my time. Probably not. Probably not, because I already forgot. Yeah. So the SWR is for you to okay. So when when your antenna is receiving at the target frequency, it will have a very, very low SWR, and it's 50 ohm. But when the antenna used is not receiving the target frequency, the impedance will change. Okay, that's why the SWR is no longer 1 to 1 or 1 to 4 or very low value. It will increase like to 1 to 2, 1 to 5. Okay. So you see there is a red zone, right? So 1 to 2 is already a very it's the boundary. It's the boundary. So if your SWR exceed 1 to 2, it will red zone, and it will have a reflected power which may risk damaging your machine. Okay. So how much reflected power is for SWR 1 to 2? It's about when you emit 100 watts forward, when the backward power is 4 watts, then the SWR is 1 to 2. Yeah, you can calculate it on your own. Yes. So if try to minimize the SWR meter is of course it will consume electricity. Okay. It's connected between the transmitter and the transmission. Actually, the transmission line means the antenna. Connect between the transmitter and antenna. Okay, and it helps you monitor the status of your power. Okay. Okay. Yeah. It requires a minimum amount of power, so you can just you don't need external power source. Okay. Oh, this is just a joke. I put it here. Testing setup. Curve of antenna. So you see that when you like there is 3 different antennas here. I'll use A as an example first. Okay, A. No, just a minute. I use B. B. This one is B. Okay, the middle one, the B. So you see that the resonance frequency is 725 kilohertz, around here, right? So it have a very very low SWR, standing wave ratio. So yeah, it is good. So for antenna A, it is too long. It's too long. Okay. Yes, they may ask you if the frequency is too I'll show it this way. They will give you an antenna like this. They may give you questions like this. My antenna at which frequency is having a SWR ratio like 1 to 5, 1 to 1.5, and other frequency it is like 1 to 3. Should my antenna be shortened or lengthened to receive a target frequency? Okay, they may ask you questions like this. Like this one. Yes. Yes, so you see they may give you antenna A and ask you, hey, I'm going to receive 40 meter band, 7125 megahertz, kilohertz. Should I lengthen the antenna or shorten the antenna? So in this case, the resonance frequency is too low. It's too low. You want to increase the frequency, right? So to increase the frequency, you shorten the antenna, you trim the antenna. Okay. Why? So you have to recall yourself F equals to C over lambda, the equation. When frequency increases, wavelength decreases. Yeah, and resonance C, yes, is too short, and you should lengthen it. Okay. Antenna length mismatch. So I've really found this description in my in the textbook. If the dipole antenna should be exactly half wavelength dipole antenna, but the impedance, the characteristics impedance of the dipole antenna is 73 ohms, but in some textbooks they say that 72 ohms. Never mind, both of them are acceptable. Okay. if you are not using the exact 1/2 wavelength to receive the frequency, it will have a complex impedance with inductive or capacitive loading effects. So that's the resistance, the impedance changes. That's why that is where we say it is no, the impedance no longer matches. Okay. Like this one. The antenna, dipole antenna should be 1/2 lambda. If it is too long, what should I do? If it is too short, what should I do? Yeah. And this concept is actually antenna tuner unit. Antenna tuner unit. Okay. Antenna tuner unit. You see that this is an open up structure. Actually, it got a variable inductor and variable capacitor. Okay. So by tuning your loop here, you can actually add capacitance or add inductance to your antenna system, so that it can helps to helps your antenna, even if it is not receiving the not exactly receiving the 1/2 lambda wavelength, it can help you to minimize your signal standing wave ratio. Yeah. So the antenna tuner unit helps to minimize your reflected power without changing your length of antenna. So sometimes if you have a very big setup, like in our HARTS CSSC, we got a like 10 meters antenna, you can't tune it, right? You can't just pull out, lengthen it or shorten it. So we make use of the antenna tuner unit. Yeah. So this is the wiring station. This is how we do it. Okay. Station wirings. So I've got 2 examples with me. They're actually the same. What I want to show you is when I was doing transmission, I will have my transmitter connected to a SWR meter, and then followed by an antenna tuner unit, and then with antenna. So the antenna is connected to ATU directly first, and transmitter is connected to SWR meter directly, and you connect the SWR and antenna system together. Okay. So that why SWR should not be put at the end, at just below the antenna, is because the antenna unit helps to calibrate, like think in a calibration way, helps to tune your antenna. So if your SWR is put before the antenna tuner unit, the antenna you are not measuring the SWR after placed after the antenna tuner unit. The antenna tuner is not showing it works yet. Okay, so your SWR to your transmitter is not accurate. That's why transmitter to SWR, antenna to antenna tuner unit, and then you connect both of them. Yeah. Yes, this is one more example. Transmitter to SWR unit, SWR meter to antenna unit, and to your antenna. This is how you do the whole simplest form of setup. So if you have a even more complicated setup, like this one, you have a transceiver, your radio connected to your amplifier. Sometimes your signal is not strong enough. You want to push, your devices may need a very high power, like you want to have over 1000 watts, then you can't just use your transceiver. You must apply your amplifier, okay, and your power meter to keep on monitoring what is your power now you are now transmitting. In our radio room, our power unit is connected. Our inverter is connected with a power meter directly, so you can just monitor the power output instead of to check the power directly. and the tuner, antenna tuner unit to help you to minimize your SWR by adding inductance or capacitance. Yeah. And sometimes if you want to check your setup, you connect it to a dummy load. Okay. So antennas is from time to time. Okay. For a dipole antenna, it is a balanced system. So if you did a balloon, balance to unbalanced converted balloon, to convert the balanced signal into an unbalanced signal so that it can be transmitted through your coaxial cable. The coaxial cable is unbalanced. Okay. Okay. Easy. So we have completed our measurement. Yeah. So we have talked about what type of instrument can be used, how to measure the DC power, RF power, current, operations, dummy loads, their purpose, how to construct it, what is standing wave ratio, what is oscilloscope, to examine the waveform and monitor. Oh, FF modulation, I didn't go through it, but FF modulation I should go through it in my last lesson. The deep oscillator I have also helped you, and have even more frequency counter, and this one. Spectrum analyzer. Yeah. Okay. So, are there any questions? Questions on measurement? No questions? No questions. Really? I don't know. Okay. So before we end our lesson, we got 30 minutes left. Let's talk about logic circuits. And I hope I have some time to go through the FET, field emission. What is FET? I forgot the whole name. Yes. Field emission, FET. Field effects transistor. Okay. So let's go through the logic circuits first. Okay. Logic circuits, it is actually not that difficult. So the basic concept is we try to use 0 and 1 to represent all the status, like Morse code, right? It's in bits and dots. Actually, it is a longer representation of 1 or shorter representation of 1. The bit means a pulse signal of 1, and a dot means a longer signal of 1. So if at any time point you don't have a signal, it is 0. So Morse code makes use of the binary system. So you can use the Morse and do the decode, and you know what is the signal behind. Okay. So you see that on the on and off conditions, or the space and the mark. Okay. CW and LTTY. Yeah, we make use of the binary system, and also in computers we make use of binary system base 2. And how to do the calculation? From binary to decimal. So the binary, they will give you a 1000011, that kind of calculation. So we go to the last digit for never mind, last digit. Last digit is 0 to the power 0, 2 to the power 0. 1 times 2 to the power 0, and so you see that there are 7 numbers, right? So 2 to the power 0, 2 to the power 1, 2 to the power 2, but to the 8th number, 2 to the power 7. Okay? 0, 1, 2, 3, 4, 5, 6, 7. Okay? And hey, if I have a 1 here, just multiply by 1. If I don't have a 1 here, just multiply by 0. Okay? And finally, you add all the numbers up. Add all the numbers up. Okay? So this is how you do the binary to decimal. But if you have a calculator, you don't need to do this kind of calculation. the calculator can help you do the conversion. Yeah. So see if I have time next lesson. Next lesson will be a quiz. So if you have time, try to do your revision. After the quiz, I will start doing the revision, 2 lessons. Okay. And any other stuff? Let me think. Yeah, you can bring your calculator with you. Bring your calculator with you, and I will show you how to do the conversion first. In your calculator, you got a mode to convert binary system to oct, which is oct, hex, and decimal. Okay, hexadecimal. And if they give you a base 10 number, which is decimal number, you can, how do you do change it in binary? Apart from doing the using the calculator, you divide by 2. Okay, 100 can you divide by 2, divide by it. Do the long division until you have 1 left. Okay. So once you do the calculation, you put all the remainders together from the bottom to top. Okay, from the bottom to top. The first digit is, this one is the first digit. Okay. 11001000. So this is 100 can be represented as 11001000. Okay. Just by doing the long division and starting from this value and all the remainders. Yeah, this is how you do it. And if you want to check your numbers, check your calculations. Hey, do you still remember that this digit? How can I change it back to decimal? This digit times 2 to the power 0. This digit times 2 to the power 1. This is 2. 1, 2, 4. This is 4. This is x0, x16, 32, 46, which is 46 plus 32 plus 4. What is the value? I'm有啲迷糊啊！我攞個 iPad 出嚟先啦。因為呢 part 好似有考一條嘅，你記到if you can memorize it, just memorize it. But if it is very hard to you, then try to memorize the concept instead. Okay. Okay. For example, in our example, it is. Never mind. I will do the calculation myself. 100. So divide by 2, 50. Divide by 2, 25. Divide by 2, 12. 2, 6. So you do it this way. So the number will be 110100 base 2. This is how you do the work. Okay. So if you want to do it in reverse way, like how to do the conversion in this way. Okay. So you do it one by one. 110 So this is 2 times 0, 0 times 2, oh, this is simply 0. 486。110哦，漏咗個零啦。 So how to illustrate this one? For 0, you multiply by 2 to the power 0. So it is 0, right? 0 multiplied by everything is 0. Okay, this one, 1 multiplied by 2 to the power 3 is 8. 1 multiplied by 2 to the power 5, 32. So you can calculate. 64， 呢個咪計錯數咧？真係計錯數。計唔翻100添。咦？點解會咁咧？110，哦，咦係喎，傻咗添。Just a minute。因為呢度，喂，110，110，係啦。咁呢度就咁樣驗算，就係，喂。So I can do the calculation now. 64 plus 32 plus 4, which should be 100. Okay. So this is how you do the calculation. Yeah, easy, right? Yeah. This is how you do the calculation. Yeah, but when at the time when I do the exam, I just use a calculator and get the result immediately. Yeah, I don't do any stuff. Circuit. There will be one question asking the circuit. So if you after your revision, you think you still have time or you already understand it, you can take this question. Otherwise, you just guess it, okay? Just guess it. And we have different symbols. Buffer means 0, 1, 0, 1. So this symbols actually looks like amplifier. So amplifier in the circuits, yeah, it is buffer. So it does not process the signal. It does not change the context of the signal. I should put it this way. The context is not changed. 0 input is still 0. 1 input is 1. Okay, buffer. Not gate, it inverts the signal. 0 input, 1 output. 1 input, 0 output. Or gate, if their A or B is 1, or both of them are 1, your output will be 1. Okay. And gate, if and only if A and B is 1, the output will be 1. Okay. You need both of them to be 1 at the same time. Okay. Exclusive OR. Why I put exclusive OR here is because it is very similar to OR, but why I say exclusive is because when both A and B is true or 1, the output will be 0. It's only true when A or B is 1. And exclusive OR is actually used in our mathematics many times, especially for cryptography. I'm not going to go through it, but yeah. And OR gate, which is OR gate plus an AND. Plus a not. So it's just flip the signal. So OR is 0, 0, 0, 0, 1, 0, right? So for an OR gate, 0, 0 will be 1. 0, 1, if A or B is 1, all of them will be 0. Yeah, just connect both of them. Not an AND gate, AND gates plus not gates. So it is AND gate with the output flipped. 0, 0, 1, 0, 1 will be 1. 1, 0 will be 1. 1, 1 will be 0. Yeah. It's exclusive and OR gate. So you know that's how to do the exclusive OR. Then you just flip it. Okay. The note here is just a NOT gate to flip the signals. So the hardest part will be identifying the gate. Okay. AND gate, OR gate. You see the shape here is different. Okay. AND gate, the shape here is different. And NOT gate, they have a knot here with a triangle. Okay, and this is all the symbol that you have to know. And exclusive or has a tail at the back. And series is just AND or others with an extra NOT gate added. Okay. And in our reality, we will have ICs. Okay, like this 4077 is X and OR gate. Okay. So this is a 4-channel IC. So that they have 4 different X and OR gates to choose. So you don't want to use the very, very basic that kind of stuff to develop your logic circuits. You can just use IC directly. It helps you save a lot of time. So which you can check which logic gate you want to use and just purchase the corresponding signal. Exercise. We don't have enough time to go through the rest of the materials. So our lessons will end here. So if you want to do the exercise, yes, you can do it. This is the answer, okay? So you can try it yourself. If you really want to attempt this, what is this? What? Yes, the AND gate, the Boolean logic, okay? Yeah. At most, in my exam, the most complex form will be this one, okay? You won't exceed this form, okay? Yeah, no more than that. So if you can already handle this complexity, yes, you can score one. You have one score in your exam. Yeah, one score, really one score. They don't ask you more than that. Okay, so I've also go through the logic circuits, and hope you can handle with it. So for the extra stuff, I will leave it to the if we have time, next lesson. So next lesson we have quiz. If you have time, do the revision first, okay? And are there any more? Yes. I will provide the notes, the slides to you. I will have a compilation so that you don't have to search every link from time to time. I will have lesson 1 to 11 all in one. Okay? And yeah, one more things to add. I have already updated my YouTube channel. So if you forgot what is the channel, let me know. Why I have to say so is because just a minute. YouTube 工作室 great. Because I've already uploaded the stream archive and the edited version of the classes, the previous classes. So if you accidentally miss one of them, you can go and listen to it. Okay. But if you want the raw one, the one record in Teams, you can go to this stream archive for to listen to it. Yeah, because this one is for public, and I've trimmed some contents. Yeah. Okay. So this is the end of our class. Thank you for coming today. So if you have any questions, feel free to WhatsApp and let me know. Okay. Remember to bring your calculator, pen and pencil to your class next time. Yeah. Okay. I have prepared 40 questions for you. So if you have your noting system, bring it with you. We can do it open book. That's okay. Yeah. Thank you. Bye bye. Because I've already uploaded the stream archive and the edited version of the classes, the previous classes. So if you accidentally missed one of them, you can go and listen to it. Okay. But if you want the raw one, the one record in Teams, you can go to this stream archive for to listen to it. Yeah, because this one is for public, and I've trimmed some context. Yeah. Okay. So this is the end of our class. Thank you for coming today. So if you have any questions, feel free to WhatsApp and let me know. Okay. Remember to bring your calculator, pen and pencil to your class next time. Yeah, okay. I have prepared 40 questions for you. So if you have your noting system, bring it with you. We can do it open book. That's okay. Yeah. Thank you. Bye-bye.